Hi guys, we meet again in a new video for chapter 2. So for our lesson today, we'll be covering our lesson on atomic structure, and our subtopic is 2.1 Bohr's atomic model. As you know, we have learned before a few parts of Bohr's atomic model. So in this video, our focus is on calculation that related to the Bohr's atomic model. So how the calculation is done? Now on the slide, we have example of question on the calculation of Bohr's atomic model. So I will show you how to solve each of the problem. So the first question is, how much energy is released when an electron falls from fourth energy level to the second energy level inside a hydrogen atom? So in this situation, show that an electron makes a transition from fourth energy level to the second energy level. And when electron make a transition from higher energy level to lower energy level, energy is released in form of photon. So the amount of energy released can be calculated by using the equation delta E equal to Rydberg constant times in bracket 1 over n1 squared minus 1 over n2 squared, where n1 is the initial energy level and n2 is the final energy level. So for this case, n1 equal to 4 and n2 equal to 2. And now we substitute the value of Rydberg constant for energy, 2.18 times 10 to the power of negative 18 joule, and values of n in the equation. Now let's solve this calculation. So the final answer for delta E is negative 4.0875 times 10 to power of negative 90 joules. So this is energy that released by electron when an electron falls from fourth energy level to the second energy level. So why the value of delta E is negative? This is because when an electron falls from a higher to a lower energy level, energy is released, indicated by the negative sign. Now let's look at the next part of this question. 1b. What is the frequency of this photon? We need to determine the frequency of the photon. To solve this question, we are going to use the value of delta E obtained from the previous question, and by using the formula delta E equal to h nu. Then we rearrange the formula, become nu equal to delta E divided by Planck constant. And now we substitute the values of delta E and Planck constant, where delta E equal to 4.0875 times 10 to power of negative 90 joules divided by 6.625 6 times 10 to power of negative 34 joule second. So take note that the value of delta E used is positive because the frequency cannot be negative. So let's solve this calculation. So the final answer for this question is 6.17 times 10 to power of 14 per second, or you can use hertz for the units. Okay, next have a look at last question, number 1C. For this question, we can use two formula, either delta E equal to hc over lambda or nu equal to c over lambda. Thus, for now, I choose the second formula to calculate the wavelength. And now we rearrange this formula become lambda equal to c divided by nu. So let's substitute all the values inside this formula. As we know, c is speed of light, which is 3 times 10 to power of 8 meter per second, while nu equal to 6.17 times 10 to power of 14 per second that we already calculate just now. So the answer is 4.86 times 10 to power of to negative 7 meter. But look at question again. The wavelength that we need to calculate should be in nanometer. So how to convert meter to nanometer? So as we know, 1 nanometer equal to 1 times 10 to power of negative 9 meter. Now we convert 4.86 times 10 to power of to negative 7 meter to nanometer by divide with 1 times 10 to power of negative 9 meter. And the final answer is 486 nanometer. Next, we proceed to the second question. Calculate the wavelength of the second line in Paschen series. Let's revise. What is the ground state for the Paschen series? As we know, ground state for the Paschen series is n equal to 3. So for this question, the second line in Paschen series produced when n electron make a transition from 5th energy level to the 3rd energy level. So now we can calculate the second line in Paschen series by using the Rydberg equation. 1 over lambda equal to RH or Rydberg constant times in bracket 1 over n1 squared minus 1 over n2 squared. For this formula, n1 should be less than n2. Therefore, n1 equal to 3 and while n2 equal to 5. So let's substitute all the values inside the Rydberg equation. The Rydberg constant that we use here is 1.097 times 10 to power of 7 per meter. So let's solve this calculation. For 1 over 3 squared equal to 1 over 9, and 1 over 5 squared equal to 1 over 25. So answer for this calculation is 7.8 times 10 to the power of 5 per meter. Now we rearrange the formula because we need to find the value of lambda. And finally, the answer is 1.282 times 10 to the power of negative 6 meter, or 1282 nanometer. Okay, we proceed to the last question, number 3. An electron in the hydrogen atom makes a transition from a higher energy level to n equal to 3. If the photon emitted has a wavelength of 1283.45 nanometer, what is the value of n for the higher energy level? Firstly, let's extract the information from the equation. The first information that we have here is n equal to 3, which is the ground state, and the wavelength of the photon emitted is 1283.45 nanometer. So we need to find the value of n for the higher energy level. Thus, by using the Rydberg equation, 1 over lambda equal to RH times in bracket 1 over n1 squared minus 1 over n2 squared, and 1 should be less than n2. So for this case, n1 equal to 3, while n2 the higher energy level that we need to find out. Next, substitute all the information given in the question. But be careful here, guys. The unit of Rydberg constant is in per meter, so we need to convert the unit of wavelength from nanometer to meter. So 1283.45 nanometer equal to 1283.45 times 10 to the power of negative 9 meter. So let's solve this calculation. So the answer for this calculation is 4.99 that approach to 5. Therefore, the higher energy level n equal to 5. That's all for this subtopic. Thank you for listening. Don't forget to attempt the formative assessment before this hour ends to secure your attendance in this lecture. Good luck and goodbye, guys.